I would like to now introduce Dr. Nicolas Pelletier with Agriculture and Agri-Foods Canada. The title of his talk is Wildfire-Driven Mercury Mobilization, Exploring the Impact on Canadian Subarctic Lakes. Welcome, Dr. Pelletier.
Thanks, John. Thanks for the presentation. You'll see I choose a quite different route for my talk. It's going to be a very broad overview of the topic of wildfire-driven mercury mobilization cause and some overview of the context surrounding that. So I work on subarctic lakes. There's 90% of what I'll discuss today is applicable to any lake, but my focus is still on this subarctic lake. And contrary to the Arctic, you won't find a universal definition of what the subarctic is, but what I refer to is this fairly large band of territory up north that's dominated by the boreal forest, although there's other biomes present, such as tundras and plains. And it's also the area where you get sporadic to discontinuous permafrost, so in green and yellow on the map. The research I did during my PhD was done on lake of the western portion of subarctic Canada, specifically in the territories of Yukon and Northwest Territories. And so I will cover the research I did during my PhD, but I had a very hard time sticking to only this because there's so much new research that's been done in the relationship between mercury and wildfires, and specifically for lakes too. So I will cover also a lot of the recent research, not only mine. The Yukon and Northwest Territories is a land of water. It's where fresh water is ubiquitous and of the uttermost importance. It's an area that has a very high density of freshwater system, lakes, river, wetland. Also hosts some of the largest lakes in North America and by extension in the world. It's also a place where freshwater fishing has been traditionally important for all local populations, especially for the First Nations living there. This is why studying and monitoring mercury in this freshwater system is still very relevant. It's also a land of fire, being dominated by the boreal forests. Fires are very frequent, and they're actually a normal part of the forest regeneration cycle. Without those wildfires, the cold temperature and the specific plant material we find there would lead to pelletification, process by which organic matter accumulates, nutrient becomes unavailable to vascular plant, and this leads to the transition of forest systems to bogs. Now, there is strong evidence that fire regime in the boreal forest and in the subarctic Canada in general has been shifting and will continue to change in response to climate change. I'll place some of these evidence on this scale that goes from observation in the paleo records, namely the peat cores and the lake sediment records, up to observation in satellite and recent aerial image in recent decades. So we know from charcoal records, mostly in lake sediments, but also in some peatlands, that in central Canada, which encompass the Yukon and Northwest Territories section that I've studied, the fire return interval was the fastest, and the fire size was largest during the Holocene thermal maximum between 9,000 and 6,000 years before present. The zero on this graph represents 0 Cal BP, so 1950. That's why you don't see change in the last 7 decades here. So the Holocene thermal maximum was a period considered warm for the Holocene with a temperature anomaly of about 0.7 Celsius. But in comparison, this is still 0.3 Celsius degree below the temperature anomaly of the last decades, which means in current years, we are likely to observe faster fire return interval, larger fires than ever since the last glaciation. We can actually see that trend from recent observation, mostly from satellite image. Since the 1960s, fire return interval have diminished, burn area have increased, fire size have increased, all indicating that fires are becoming more frequent and more severe in Canada in general, including subarctic Western Canada. And when you put all that together, it means that if current condition persists, fire activity will be unprecedented in the context of the last 8,000 years, at least. So what does that mean for mercury? Well, as they accumulate carbon and organic matter, boreal forests also accumulate mercury over a long period. You can see this in the paper highlighted on the left-hand side here, where you can see a good relationship between the time since the last fire and the mercury content in the boreal forest soil. And so, of course, if this relationship exists, it's because a wildfire released at least some of that mercury that's accumulated over a very long period. We also know that peatlands, specifically, which are very common in subarctic Canada, are a hotspot for the accumulation of mercury as they accumulate organic matter. And we know from recent observation and modeling that peatland, which for a long time acted as fire breaks, when in state of drought, actually become fuel for wildfire. And so this graph here on the right-hand side shows predicted carbon loss to wildfires from Arctic boreal peatland under different climate scenarios. And of course, these can be equated to proportional mercury losses. So what happens to mercury during those fires? During a wildfire, the temperature goes above 1,000 Celsius, which is largely sufficient to decompose the metal humic bound that holds mercury. All of the laboratory study, the control burn, the mass balance approach, they've all indicated that during the fire, mercury can be almost completely released from soil organic matter and from vegetation. Over 85% of the mercury is released from vegetation, over 75% from the soil. And most of that mercury will be released in the atmosphere, either through particulate-bound mercury or in gaseous form. And the ratio between these two generally depend on the burning condition and the type of vegetation, with higher moisture content leading to more particulate-bound mercury. But normally, the gaseous form of mercury are by far exceeding the particulate-bound form. But there's also a small fraction of mercury that will remain in ash and charred organic material. There's also some particulate-bound mercury that will be redeposited locally. And there's also mercury that will be quickly reabsorbed to ashes and charred organic material following the fire. And this is all mercury forms that are susceptible to be transported and remobilized toward aquatic ecosystems. We think more about lakes. There's three main pathways for mercury to accumulate in the lake because of a wildfire. The first one would be short-range atmospheric deposition. This is mostly the particulate-bound mercury form, which tends to be deposited at closer distance from the fire. Then there's long-range atmospheric deposition from wildfires that occur at the global scale because the gas form of mercury have a very long atmospheric residence times. But the most important fluxes are potentially caused by catchment transport. And this is the transport of all the remaining mercury, the mercury that's locally redeposited, and the mercury that's reabsorbed after fire. I see two different impacts from long-range atmospheric deposition. So these create plumes that travel very long distance, as depicted on the left-hand side map from Fraser and colleagues. First, a fraction of these plumes will be deposited directly onto lake surface as it is oxidized to mercury 2. And it can temporarily increase wet deposition everywhere under that plume, but these are quite small fluxes. Secondly, any source of atmospheric mercury pollution, of course, are retained in part in lake catchment, and then they'll be delivered subsequently to the lakes in stream by catchment transport. So in the study from which the right-hand side diagram was taken, we were not looking specifically at wildfire impact, but what we found was applicable to any long-range pollution forms. We used the flux deconstruction approach in lake sediments that were finely dated to estimate the proportion of mercury accumulation that was attributable to anthropogenic pollution. And we compared those fluxes in lakes to those of nearby umbrotrophic peatland, where a similar flux deconstruction approach was used. And these are peatland that are disconnected from groundwater and surface water. So they receive input solely from the atmosphere. And so they accumulate mercury also only from the atmosphere. And we found that catchment accumulate mercury pollution from local and long-range sources and transport it to the lake for years following the peak in deposition rate. And moreover, the driving force for the accumulation of this excess mercury become related to catchment-related dynamic more than the timing of the initial deposition. And so wildfires can be one of these catchment-related dynamics. So are permafrost thaw, increasing soil temperature, change in the snow melt timing and duration, and multiple other climate-related factors that we are seeing along with climate change. For the short-range deposition in 2020, to study this impact for the subarctic lake, we analyzed lake sediments from a few small lakes just on the outskirts of major wildfires. And these lakes are in a very flat landscape. So we assume, and they are very small too. So we assume that variation in catchment influence over time were minimal. We used a superposed epoch analysis in the fine scale dated sediments record to evaluate if there was any concurrent peak in charcoal influx, which indicate wildfire fallouts, and mercury accumulation rate. Actually, we looked at a large number of metal and major ion. The superposed epoch analysis we're using aims at obtaining a composite response at different time lag around discrete events. And in this case, the discrete events were wildfires. And so you can see the impact on mercury on this last graph here. We found that the peak of mercury occurring during the wildfire fallouts was barely significant. It was very small, very short-lived. It's actually significant only for the year where the fire was observed. And compared to most other metals that we've analyzed, the flux of mercury were among the least impacted by wildfire fallout. Nevertheless, they were detectable. It was an average flux of 0.1 microgram per square meter per year. And that for these lakes represent a 5% increase in total mercury accumulation on average. One of the major impact of wildfires on lake system is to increase sediment loading by degrading the ability of the catchment to retain sediments and organic matter. So in this study from 2022, we looked at the impact of major wildfires occurring at short return interval in some mountain lakes of Yukon. We hypothesized that there would be large metal fluxes following a fire that occurred in 1998, only 40 years after another fire in 1958. We've compared 4 lakes in the same valley. These lakes represent a gradient of exposure to wildfire in the last 100 years. And we found a clear link between fire return interval and the current state of soil and vegetation. There was little to no vegetation recovery observed around Little Fox Lake. These image here, so this side of the lake has burned twice, this one did not. You can see a very thick mat of organic matter and sphagnum that subsists on this side of the lake, while this one has barely any organic matter layer and barely any vegetation recovery. As a result, while sedimentation rates have increased by 3 to 5-fold in Little Fox Lake, especially after the last fire in 1998. So in comparison, sedimentation rate remains stable or increased by only 1-fold in most other lakes of the same valley. This led to a concurrent increase in the flux of mercury. In that case, as I said, it's the rate of sedimentation that changed a lot, but also the concentration of mercury in the sediment at increase in response to wildfire. Again, we used a flux deconstruction approach to estimate the proportion of mercury that was attributable to anthropogenic pollution. And we saw that this flux increased with the onset of mercury pollution during the Industrial Revolution, but is also remobilized in recent years by the effect of wildfires. And we attributed the faster rate of erosion in that case to, well, obviously the loss of vegetation and soil organic matter, which decreased by a lot the water retention potential in the catchment. But there's also an impact of the hydrophobicity of charcoal and ash, which further reduce the water retention potential and increase the surface water flow rate. So in this research, we really highlighted like an extreme case with large wildfires, short return intervals, steep slope gradients, but we can imagine that a similar phenomenon can occur at lower magnitude catchments that are less steep. And for the fire severity and return interval part, we saw from the paleo records and recent observation that this type of situation has become more frequent and will persistently be more frequent in the future. So in the previous study, I focused on the interpretation of the transport of solids and solid-related mercury, but there's also an important relationship between dissolved organic matter and mercury for catchment-related input. We saw pretty consistently in the literature that there's an increase in aquatic system dissolved organic mercury post-fire. And we know that mercury complexes with dissolved organic matter. So obviously there are transport pathways shared by these two compounds. There's also one very recent evidence that show that mercury will bound to dissolved organic matter preferentially. So mercury will bound to char after the fire, but in greater concentration of dissolved organic carbon in a solution, mercury will bound more slowly and less efficiently to charcoal and ash. And so this is a good indication of the relationship, the importance of dissolved organic carbon for mercury transport. Although the relationship is not straightforward, there was a recent study that showed that in a recent mega fires, they studied the dissolved organic carbon and mercury in the stream going through the fire, and they actually saw a decrease in stream dissolved organic matter following the fire, and they attributed that to very high fire severity. Which brings me to the topic of fire severity and the impact of fire severity on Lake Mercury, which is really not straightforward, and I think more research is needed on that. There are some simultaneous processes that need to be disentangled for that. So if you think on the one hand, a greater fire severity would lead to more volatilization of mercury, which would lead to lower concentration of mercury remaining in the soil. But it will also lead to more soil organic matter loss and slower vegetation recovery, which would increase the transport of the remaining soil organic matter. So on the other side of the equation, you would think a lower fire severity leads to less volatilization, more stable mercury and black ash, more reabsorption of mercury, which lead to more mercury that could be transported to the lake. But at the same time, if you have more vegetation and soil organic matter to slow down the transport of mercury, it's really unclear what the net impact of fire severity is on Lake Mercury. One indirect impact of wildfire in subarctic environment is its interaction with permafrost. So since the subarctic is where you get sporadic and discontinuous permafrost, it also means that's where some of that permafrost is at the in equilibrium with climate. Moreover, the recent increase in temperature from climate change causing even larger area to be included in those fragile equilibrium situation. While wildfire removes tree cover that provide protection from insolation, it will decrease the thickness of soil organic matter layer, which provide insulation, and it will darken the surface of the soil, which reduce albedo. So the most up-to-date model suggests that some lowland boreal forests and peatlands will remain resilient to wildfires, but a lot of upland area with thin organic layers and some dry soil will experience rapid and irreversible permafrost degradation. So this has important consequences for mercury because for mercury transport to streams, lakes, the Arctic Ocean, because we know that thawing permafrost release soil mercury that's transported along with the soil organic matter and particulate mercury. On a final note, I just want to, maybe that's a positive note, maybe not. It seems that the impact of wildfire and mercury reactivity and to form methyl mercury and the impact on biota may be limited. However, the research on that topic is getting dated, so it may not be accurately representing the unprecedented fire regime we are experiencing right now with more severe, more frequent, and larger fire. The research, though, that exists suggests that there's very low amount of methyl mercury that's formed and transported to lake following fires. Most often, there's no significant impact on mercury concentration in macroinvertebrate and fish. When there is an impact that's observed, it's attributable to food web reconstruction because of nutrient inputs, not mercury input. But there are potentially some possible interaction with sulfur in the soil or mercury that's reabsorbed into ashes that could promote a specific condition for methylations. Also, some heavy rainfall that occurs close timing to the fire could also be a good source of methyl mercury. But really, a lot more research is warranted on that. So I'll just leave that slide for conclusion here because I think I went over my time by a bit. I'll leave that for the discussion session and just want to acknowledge my PhD supervisor, a bunch of funding sources, and all the government authority that allowed us to do the research. So thank you.